Good morning, everybody. This is Professor Mousa Bani from Al Ain University, United Arab Emirates, on behalf of my colleagues. I'm presenting our paper entitled Design-Oriented Charts for Passive Earth Pressure for Normally Consolidated and Over-Consolidated Sands in Homogeneous and Stratified Profiles. Importance of our study is that the passive earth pressure KP is critical for designing retaining walls, anchor blocks, and deep foundations. The problem, conventional theories, column ranking, rely on simplified assumptions like planar failure surfaces and homogeneous soil. However, real-world conditions often involve layered soils and stress history. That's over-consolidated soils, which these theories do not fully address. So our goal is to bridge the gap between complex theoretical soil mechanics and practical engineering design. Why did we undertake this study? As engineers, we know that estimating passive earth pressure is vital for the safety of structures like retaining walls. However, the classical theories we use, ranking and column, are often too simplified. They assume the soil is uniform and often ignore stress history. In reality, we deal with layered soils and over-consolidated sands. Our goal was to create a tool that accounts for these complexities while remaining easy to use in daily design practice. Methodology. Framework is a theoretical framework based on limit equilibrium analysis, and the scope, the soil type is sand cohesionless, the profiles homogeneous and two-layered systems, the states normally consolidated NC and over-consolidated OC soils. Key innovation, introducing a composite shear angle that is nu phi. And modified failure mechanism for stratified profiles. Failure mechanism in layer soil. We have two cases. Case 1, strong sand over weak sand. The failure plane passes through the lower weak layer, as we see in figure 1, forming a deformation zone. It then extends to the upper strong layer, forming a passive ranking zone, which is supported by experimental work performed by Khoury in 1994. The second case is a weak sand over strong sand. Failure plane is confined to the upper weak layer, as we can see in figure 2, and does not penetrate the strong underlying deposit. The theoretical formation. The composite friction angle phi nu used to characterize the deformation zone in layered profiles. So we consider phi nu equals to tan inverse tan phi 1 plus tan phi 2 over 2. And for ranking zone calculation, the upper layer uses the upper layer friction angle phi 1, incorporating OCR, that's the over consolidation ratio, into the coefficient calculation. The proposed method is extended to find the passive earth pressure coefficient for this case by adding new assumptions, as shown in figure 3. Ranking zone will occur within the upper layer, so that the upper layer's internal friction angle phi 1 will be considered to calculate the passive earth pressure coefficient for ranking zone. Here is question number 1, how to calculate the K-passive for ranking, while OCR represent over consolidation ratio, phi1 angle of shearing resistance of the soil of the backfill for the upper layer. Understanding the failure mechanism is crucial. We observe two distinct behaviors based on layer strength. In the first case, where you have a strong layer over a weak one, the failure plane is deep. It cuts through the weak bottom layer before moving up. However, in the second case, weak soil on the top of very strong soil, the failure is shallow. It stays trapped in the top layer. Our theoretical model distinguishes between these two physical realities. The deformed zone will occur in both layers, in the upper one and the lower one. Then a new internal friction angle will be composed of two layers, considering the weight as a proportionate combination of the weight of the respective layers within the slice. This new proposed angle is given in the following formula. While phi1 is the upper layer soil friction angle and phi2 lower layer soil friction angle. This angle will be replaced instead of the internal friction angle of the homogeneous backfill for the deformation zone in equation 3 and 4 and 5 for the last slice base inclination alpha n, which is represented by this formula, where phi angle of shearing resistance of the soil, alpha 1 first slice base inclination, delta 1 is inter-slice frictional angle for the first slice, and theta 1 angle of first slice from the backfill surface. The computer program was adjusted to consider the previous assumptions. In this analysis, a wide range of parameters were also used to develop design charts for practical use and to be easy for engineers to use as well. Here is the KI for any slice, and where these parameters are illustrated. And finally, alpha n is also given in this equation, number 6. The development of design charts, normally consolidated and over-consolidated, homogeneous, and two-layer sand. The design charts were constructed and they are simple and easy to use for practical purposes, taking into consideration the normally consolidated and over-consolidated soil with wide ranges of internal friction angles and soil wall friction angles. The purpose is to eliminate the need for complex equations during routine design. And the parameters covered in this modeling: internal friction angle of upper layer, phi1, and phi2 for the lower layer, soil wall friction delta, and over consolidation ratio OCR. These results show that all values of passive earth pressure of strong homogeneous sands are higher than that of a strong sand overlaying weak sand. This can be explained by the fact that with decreasing lower layer strength, it will result in a decrease in the passive pressure all over the system, because the stress needed for the weak layer to fail is much less than that for the strong layer. We process these theoretical equations across a wide range of parameters to generate design charts. These charts allow an engineer to input the friction angle of both layers, the wall roughness, and the OCR, and immediately obtain the passive pressure coefficient without solving complex differential equations. In this figure, Figure number 4 shows the coefficient of passive earth pressure for normally consolidated sand. It's given like delta phi over phi 1 equals 0, 1/3, 2/3, and 1. And also the OCR equals 2. And also the delta over phi 1 equals like different ranges from 0, 1/3, 2/3, 2, and 1. Also, phi 1 is given here, varied from like of 25 degrees to 45 degrees in all cases. Also here, it can be seen that the also for over consolidation ratio of 2, same thing. Like these figures offer easy graphs to use for design engineers with over consolidation ratio also 2, and giving like the delta over phi in different ranges as well. Again, this is another other graphs for produced charts for coefficient of passive earth pressure for OCR 4. Conclusions. The study successfully provides a series of design charts that bond complex theoretical models and practical geotechnical design for passive earth pressure. The key findings are: first, the proposed method, which uses a composite friction angle phi nu for stratified soil and defined failure mechanism, successfully captures the passive pressure behind retaining structures behavior in both homogeneous and two-layered sand systems. The passive earth pressure coefficient is maximum for strong homogeneous sand, and the existence of a weak underlying layer considerably decreases the overall passive resistance of a soil mass with a stronger upper layer. For the situation of a weak sand layer overlaying a very dense, strong deposit, the passive pressure is almost equal to that of a weak homogeneous sand, as the failure plane does not enter the lower strong layer. Fourth, the provided charts provide engineers rapid and dependable tools to assess K-passive or passive earth pressure coefficient for a preliminary and detailed design, accounting for critical factors such as soil stratification, stress history, that's the OCR, and wall roughness, delta over phi, thus contributing to safer and more efficient geotechnical applications. Thank you very much for listening, and I wish you a very pleasant day.